We've been sold a fantasy. Mars colonies, interplanetary civilization, humanity's next giant leap. But there's a problem everyone's ignoring. We don't actually know how to bring people back from Mars alive. The return journey is a nightmare of physics, biology, and psychology that could turn our greatest achievement into our darkest tragedy. And here is a question for you. What's the one thing about Earth you'd miss most during a 3-year journey to Mars? Let us know in the comments. I will pin the most creative answer. Now let's begin. When we think about space exploration, we often imagine the adventure, the discovery, the triumph of human ingenuity. We picture astronauts planting flags, rovers rolling across alien terrain, humanity taking its next giant leap. But space doesn't care about our dreams. It doesn't care about our technology or our courage. Space is indifferent. And Mars, with its thin atmosphere and weak gravity, presents a gauntlet of challenges so severe that bringing astronauts home might be one of the most difficult engineering problems we've ever faced. This is the reality that space agencies around the world are wrestling with right now. NASA, the European Space Agency, and other organizations are deep into planning human missions to the Red Planet. They're designing spacecraft, calculating trajectories, building life support systems. But there's one problem that keeps coming up, one obstacle that haunts every meeting, every simulation, every late-night calculation session. And that problem is simple to state, but fiendishly difficult to solve. How do we bring them back? The distance alone is staggering. At its closest approach, Mars is about 55 million kilometers from Earth. At its farthest, it's more than 400 million kilometers away. That's roughly 1,000 times the distance to the Moon. When the Apollo astronauts went to the Moon, their round trip took about 8 days. A mission to Mars? We're talking about a journey lasting anywhere from 21 months to 36 months, depending on the trajectory and planetary alignment. That's not a trip. That's a marathon through the most hostile environment imaginable. But distance is just the beginning. The real problems start when you consider what happens to the human body during that time. See, we evolved on Earth. Our bones, our muscles, our cardiovascular system, even the way our cells function, everything about us was shaped by living under Earth's gravity, protected by Earth's magnetic field, bathed in the light of our sun at just the right distance. Take all of that away, and the human body doesn't just adapt, it starts to break down. Let's talk about bones first. On Earth, your skeleton is constantly rebuilding itself. Old bone tissue breaks down and new tissue forms to replace it. It's a delicate balance maintained by the stress that gravity places on your bones every single day. But in the microgravity environment of space, that stress disappears. Your body, in its infinite but sometimes misguided wisdom, decides it doesn't need all that heavy bone anymore, so it starts to dissolve it. Astronauts on the International Space Station lose about 1 to 2% of their bone density per month. That might not sound like much, but consider this. A typical osteoporosis patient on Earth loses about 1% per year. Astronauts are losing bone 12 to 24 times faster than that. Now imagine you're on a Mars mission. The journey there takes about 7 months. 7 months of bone loss. Then you spend time on Mars itself. Sure, Mars has gravity, about 38% of Earth's. That helps, but it's not enough to stop the deterioration completely. Studies suggest that even partial gravity only slows the process. And then there's the return journey, another 7 months. By the time you get back to Earth, your bones could be so weakened that standing up, walking, even the impact of your spacecraft touching down could cause fractures. Some researchers predict that after a 3-year Mars mission, astronauts could develop osteopenia, a condition of reduced bone density that precedes osteoporosis. One study examining data from 69 astronauts predicted that 62% of crew members on an opposition-class trajectory lasting 400 to 600 days would develop osteopenia. For longer conjunction-class missions of 1,000 to 1,200 days, the prediction was even grimmer. 100% would develop osteopenia, with 33% at risk for full osteoporosis. Think about that for a moment. You travel hundreds of millions of kilometers, survive the isolation, the radiation, the psychological stress. You accomplish one of humanity's greatest achievements, and then you come home to a body that can barely support its own weight. But before you even reach that point, here's where you should take a second. Hit that subscribe button and give this video a thumbs up. Your engagement really helps spread this knowledge. Bones aren't the only concern, your muscles are deteriorating too. In microgravity, you don't need much strength to move around. You can push off walls, float through corridors, manipulate objects with minimal effort. So your muscles, like your bones, start to atrophy. Research from long-duration spaceflight shows that astronauts can lose up to 20% of their muscle mass during extended missions. The muscles most affected are the ones you use to fight gravity on Earth: your legs, your back, your core. These are the same muscles you'll desperately need when you return to Earth's gravity. The Mars 500 study, a simulated 520-day mission conducted on Earth, gave us valuable insights into muscle loss during isolation and confinement. 6 healthy male subjects were monitored throughout the simulation. The results were telling. While calf muscles, which contain predominantly type 1 slow-twitch fibers, showed some resilience and even strengthened with certain exercise interventions, the quadriceps and hamstrings, rich in type 2 fast-twitch fibers, showed significant bilateral loss. This suggests that different muscle groups respond differently to prolonged spaceflight conditions, and some are more vulnerable than others. Exercise helps, of course. Astronauts on the International Space Station spend about 2 hours every day working out using resistance bands, treadmills with harnesses, and specialized equipment designed for microgravity. But even with rigorous exercise protocols, they still lose muscle mass. And here's the kicker. On a Mars mission, resources are limited. Every kilogram of equipment, every watt of power, every cubic meter of space has to be justified. Can you really dedicate the room and resources for a full gym? And even if you can, will it be enough to counteract 7 months of microgravity on the way there, time on Mars with only 38% gravity, and another 7 months on the way back? Then there's your cardiovascular system. Your heart is a muscle too, and like any muscle, it adapts to its environment. On Earth, your heart has to work hard to pump blood upward against gravity, especially to your brain. In space, that's not necessary. Blood distribution changes, fluids shift toward your head, giving astronauts that characteristic puffy face appearance. Your heart, sensing it doesn't need to work as hard, begins to atrophy. It becomes smaller, weaker. Studies have shown that even with exercise, astronauts' hearts decrease in mass during long missions. When you return to Earth, your heart suddenly has to work against gravity again, but it's not as strong as it used to be. Standing up can cause dizziness, fainting, even dangerous drops in blood pressure. This condition, called orthostatic intolerance, affects most astronauts returning from long missions. Picture this. You've just landed back on Earth after 3 years away. Your spacecraft touches down, you've made it, you're home. But when you try to stand up, your vision goes dark. Your heart is racing, trying to pump blood to your brain, but it's not strong enough. You collapse. Emergency personnel rush in to help you out of the capsule because you literally cannot walk on your own. This isn't hypothetical. Astronauts returning from even 6-month stays on the International Space Station often need assistance and weeks of rehabilitation before they can function normally again. Now multiply that recovery time for a mission 3 to 6 times longer. And we haven't even touched on the biggest threat yet: radiation. Space is flooded with radiation. On Earth, we're protected by 2 incredible shields, our atmosphere and our magnetic field. These work together like a cosmic bodyguard, deflecting and absorbing harmful particles from the sun and from deep space. But once you leave Earth's protective bubble, you're exposed to radiation levels that are simply not found anywhere on our planet's surface. There are two main types of space radiation that astronauts face. First, there's solar radiation, particles ejected from the sun during events called solar flares and coronal mass ejections. These events can send bursts of high-energy protons racing through space. If astronauts are caught in one of these storms without adequate shielding, they could receive a lethal dose of radiation within hours. The second type is even more insidious: galactic cosmic rays. These are high-energy particles, mostly protons and heavy ions, that come from outside our solar system. They travel at nearly the speed of light and can penetrate deep into spacecraft, into habitats, even into human tissue. During the Artemis 1 mission, an uncrewed test flight that orbited the Moon in 2022, NASA placed radiation detectors inside the Orion spacecraft to measure exposure levels. The data was sobering. Even with the spacecraft's shielding, radiation levels were significantly higher than anything astronauts experience on the International Space Station, which still benefits from some protection from Earth's magnetic field. When researchers extrapolated this data to predict exposure during a Mars mission, the results were concerning. A round-trip journey to Mars could expose astronauts to radiation doses approaching or even exceeding NASA's career limits for astronauts. What does radiation do to the human body? The effects are cumulative and varied. In the short term, high doses can cause acute radiation syndrome, nausea, vomiting, damage to the immune system. But the long-term effects are what really worry scientists. Radiation damages DNA. Your cells have repair mechanisms, but they're not perfect. Each time a cosmic ray passes through your body, it leaves a trail of damaged molecules. Most of the time, your cells fix the damage. Sometimes they don't. And when they don't, you get mutations that can lead to cancer. Studies published in 2024 by NASA's Human Research Program identified space radiation as one of the highest priority red risks for Mars missions. Red risks are those with both high likelihood and severe consequences. The research indicates that astronauts on a Mars mission face significantly elevated risks for several types of cancer, including leukemia, lung cancer, and stomach cancer. But cancer isn't the only concern. Radiation also damages the cardiovascular system, increasing the risk of heart disease and stroke. It affects the central nervous system, potentially causing cognitive impairment, memory problems, and changes in behavior. Imagine being millions of kilometers from home, responsible for critical decisions that could mean life or death for your crew, and your brain isn't working quite right because cosmic rays have been bombarding your neurons for months. One study examining the effects of heavy ion radiation on the brain found that even low doses could impair cognitive function in ways that persisted long after exposure. This isn't just about health after the mission, it's about whether astronauts can perform their duties during the mission. Now you might be thinking, can't we just shield the spacecraft better? Add more material, thicker walls, problem solved, right? Well, here's where physics gets frustrating. The more shielding you add, the heavier your spacecraft becomes, and the heavier your spacecraft, the more fuel you need to move it. And the more fuel you need, the more that fuel weighs, which means you need even more fuel to carry that fuel. It's a vicious cycle that engineers call the tyranny of the rocket equation. Every kilogram matters. But there's an even trickier problem. Some types of shielding can actually make radiation worse. When high-energy particles hit dense materials like aluminum, they can create secondary radiation through a process called nuclear fragmentation. The original particle breaks apart atoms in the shielding material, creating a shower of smaller particles that can be just as harmful, sometimes more so. It's like trying to stop a bullet by putting up a wall, only to have the wall explode into shrapnel. Scientists are working on advanced materials, things like hydrogen-rich polymers and specialized composites, but we're still years away from having truly effective, lightweight radiation protection for deep space missions. Speaking of Mars's surface, let's talk about what happens when you actually land there. Mars has an atmosphere, but calling it an atmosphere is almost generous. The air pressure on Mars is less than 1% of Earth's. That's equivalent to standing at an altitude of about 35 kilometers above Earth's surface. No human has ever been that high without a pressure suit. And the atmosphere that does exist is 95% carbon dioxide. You can't breathe it. Step outside without a spacesuit, and you'd lose consciousness in about 15 seconds. The temperature swings are brutal too. At the equator, during the day, temperatures might reach a balmy 20 degrees Celsius. Sounds pleasant, right? Wait until night. Temperatures can plunge to minus 73 degrees Celsius or lower. Your habitat needs to protect you from these extremes, provide breathable air, maintain pressure, filter out toxic dust, and do all of this reliably for the 18 to 20 months you'll be on the surface. And then there's the psychological dimension. This is something we don't talk about enough. You're trapped in a small habitat with the same few people for nearly 3 years. There's no escape, no privacy, no relief. Communication with Earth has a delay of up to 22 minutes each way when the planets are at their farthest. You can't have a real-time conversation with your family. You can't call for immediate help if something goes wrong. You're truly on your own. Studies of isolated environments on Earth, like Antarctic research stations and submarine crews, show that prolonged isolation leads to increased stress, interpersonal conflicts, sleep disturbances, and mood disorders. NASA's behavioral health research has identified isolation and confinement as another red risk for Mars missions. The psychological strain could impair decision-making, reduce crew cohesion, and, in worst-case scenarios, lead to psychiatric emergencies. Imagine a crew member experiencing a severe mental health crisis millions of kilometers from any hospital, any trained mental health professional, any real support system. How do you handle that? What protocols do you put in place? These aren't just theoretical questions. They're real problems that mission planners are grappling with right now. By the way, if you're finding this deep dive into Mars exploration fascinating, you might want to check out my other video called Mars Was Once Like Earth. What happened to it? It explores the dramatic transformation of Mars from a potentially habitable world with liquid water and a thick atmosphere to the frozen desert we see today. The link is in the description and on the card above, and I think you'll find it really complements what we're discussing here. But let's get back to the main problem: returning home. You've survived the journey there. You've endured the months on Mars. Your bones are weaker. Your muscles have atrophied. Your cardiovascular system has deconditioned. And you've been exposed to dangerous levels of radiation. Now you have to climb back into a spacecraft and spend another 7 months in microgravity before you can even attempt re-entry into Earth's atmosphere. Re-entry is one of the most dangerous phases of any space mission. Your spacecraft is traveling at enormous speed, tens of thousands of kilometers per hour. To land safely, you have to slow down, and the only way to do that is through friction with the atmosphere. That friction generates tremendous heat. The space shuttle's thermal protection system had to withstand temperatures exceeding 1,600 degrees Celsius during re-entry. A tiny defect in that system led to the Columbia disaster in 2003, killing all 7 crew members. Now imagine going through re-entry in your weakened state. The deceleration forces, the G-forces, are intense. A typical re-entry subjects astronauts to forces of 4 to 6 times Earth's gravity. Your body, which has been floating in near weightlessness for months, suddenly weighs 4 to 6 times what it should. Your bones, already weakened from bone loss, have to support that load. Your heart, smaller and weaker than when you left, has to pump blood against those forces. Your muscles, atrophied from disuse, have to hold your body in position. Astronauts returning from 6-month ISS missions describe re-entry as brutal. They feel like they weigh hundreds of kilograms. Some have difficulty breathing because their chest muscles, weakened from months in space, struggle to expand their lungs against the G-forces. And remember, ISS astronauts have only been in space for 6 months. Mars astronauts will have been gone for 3 years. The physical toll will be exponentially greater. Let's talk about something that sounds almost science fiction but is very real. Spaceflight-associated neuroocular syndrome, or CNS for short. This condition was discovered somewhat by accident when astronauts started reporting vision changes after long-duration missions. At first, researchers thought it was temporary, maybe some fluid pressure changes that would resolve quickly. But as more astronauts spent longer periods in space, the picture became clearer and more alarming. What happens is this. In microgravity, fluids in your body shift upward. There's no gravity pulling blood and other fluids down into your legs like on Earth. Instead, everything redistributes toward your head and upper body. This creates increased pressure inside your skull, pressure that doesn't exist on Earth. That pressure affects your optic nerves and the shape of your eyeballs. Some astronauts have returned from space with flattened eyeballs, swollen optic nerves, and changes in how their eyes refract light. For some, these changes have been permanent. Studies examining astronauts after 6-month missions found that approximately 40% of them experienced measurable vision changes. Some needed new glasses prescriptions, others reported persistent blurriness. A few have permanent visual impairment. Now extrapolate that to a 3-year Mars mission. What percentage of the crew will experience vision problems? How severe will those problems be? And here's the critical question. If your vision is permanently impaired, can you pilot a spacecraft? Can you operate complex equipment? Can you navigate an emergency? NASA takes this seriously enough that SANS is classified as another red risk for exploration missions. Research published in 2025 has shown that the longer astronauts spend in microgravity, the more severe the neuroocular changes become. The mechanism isn't fully understood yet, which makes it difficult to develop effective countermeasures. Some proposed solutions include lower body negative pressure devices that pull fluids back down into the legs, or perhaps rotating spacecraft to create artificial gravity. But both of these solutions add complexity, weight, and cost to an already monumentally expensive mission. Speaking of artificial gravity, let's address what seems like an obvious solution to many of these problems. Why not just spin the spacecraft? Create artificial gravity through rotation and boom, problem solved. Your bones don't deteriorate, your muscles don't atrophy, your cardiovascular system stays healthy, fluids stay properly distributed. It sounds perfect. And in theory it could work, but the engineering challenges are substantial. To create Earth-like gravity through rotation, you need either a very large diameter or a very fast rotation rate. The smaller your spacecraft, the faster it needs to spin, and fast rotation creates problems of its own. There's something called the Coriolis effect, where moving in a rotating environment creates unusual forces that can cause severe motion sickness and disorientation. Astronauts would struggle with simple tasks like walking or throwing objects because the physics would feel wrong. Their inner ear, which helps maintain balance, would be constantly confused. A larger spacecraft rotating more slowly would reduce these problems, but building something large enough is extraordinarily difficult and expensive. You'd need to construct it in orbit, piece by piece, which requires numerous launches, complex assembly operations, and extensive testing. NASA has studied rotating spacecraft designs for decades. Some concepts are beautiful and elegant, massive wheels or dumbbells spinning gracefully through space. But the gap between concept and reality is vast. As of 2026, we still don't have a practical, affordable design for an artificial gravity spacecraft that could make the journey to Mars. So let's assume, for the sake of argument, that we solve all these problems. We develop better radiation shielding, maybe even artificial gravity. We perfect exercise protocols that minimize bone and muscle loss. We create psychological support systems that keep the crew mentally healthy. The astronauts make it to Mars, spend their time there, and begin the journey home. They survive re-entry and land safely on Earth. Now what? The recovery period is going to be brutal. Astronauts returning from 6-month ISS missions typically need several weeks just to regain basic functionality. They undergo intensive rehabilitation, physical therapy, carefully monitored exercise programs. Their bones are slowly rebuilding, their muscles slowly regaining strength, their cardiovascular systems gradually readapting to Earth's gravity. Some effects, like certain bone density losses, may never fully reverse. After a 3-year Mars mission, we're talking about months or even years of recovery. Some astronauts might never fully regain their pre-flight physical condition. There's also the question of reproductive health, something that doesn't get discussed as often but is crucial if we're serious about long-term space exploration. Radiation exposure damages reproductive cells. Studies on male astronauts have shown changes in sperm count and motility after spaceflight. For female astronauts, the ovaries are particularly vulnerable to radiation damage because eggs cannot be regenerated. A woman is born with all the eggs she'll ever have, and radiation can damage them permanently. If a female astronaut goes to Mars and receives high radiation doses, she might face reduced fertility or increased risk of genetic abnormalities in future children. These are deeply personal concerns that prospective Mars astronauts will have to consider carefully. And let's not forget about the immune system. Research has shown that microgravity affects immune function in complex ways. Some aspects of immunity are suppressed, making astronauts more vulnerable to infections. Other aspects become overactive, increasing inflammation. The stress of spaceflight combined with radiation exposure can reactivate dormant viruses in the body. Several astronauts have experienced herpes virus reactivation during missions. In a closed environment millions of kilometers from Earth, an infectious disease outbreak could be catastrophic. There's no hospital to evacuate to, no ability to bring in additional medical supplies beyond what was packed before launch. Medical emergencies are another sobering consideration. What happens if an astronaut develops appendicitis on the way to Mars, or suffers a major injury, or has a heart attack? A recent review published in the Journal of Space Safety Engineering in 2024 examined potential surgical conditions during Mars missions. The findings were stark. During a 3-year mission, the probability of at least one crew member requiring surgical intervention is significant. We're talking about everything from trauma injuries to acute abdominal emergencies to dental problems that could become infected. Can you perform surgery in microgravity? Blood doesn't drip, it floats. Controlling bleeding is extremely difficult. Sterilizing instruments and maintaining a sterile field is challenging when everything floats around. Anesthesia behaves differently without gravity. Even simple procedures become complex. And who performs the surgery? You'd need at least one crew member with advanced medical training, possibly surgical experience, but that person is also needed for other mission-critical roles. How do you balance all these requirements with a small crew? Some researchers have proposed advanced telemedicine solutions, where surgeons on Earth could guide procedures remotely using robotic systems. But remember that communication delay we discussed? 22 minutes each way at maximum distance. You can't perform surgery with a 44-minute round-trip delay for every instruction. The Mars crew would essentially be on their own for any medical emergency. That's a terrifying prospect. Now let's consider the sheer logistics of a Mars return mission. You're not just launching astronauts to Mars, you're launching everything they'll need to survive there and return home. That includes a habitat, life support systems, power generation equipment, scientific instruments, rovers, spacesuits, food, water, spare parts, medical supplies, and most critically, fuel for the return journey. The amount of fuel needed is staggering. Here's why: Mars has about 1/3 of Earth's gravity, but it's still significant. To lift off from Mars and begin the journey home, you need a rocket, and that rocket needs fuel, a lot of fuel. One proposal involves sending the return vehicle to Mars ahead of time before the crew even launches from Earth. This vehicle would land on Mars with equipment to manufacture fuel from the Martian atmosphere, specifically converting carbon dioxide into methane and oxygen. This process, called in situ resource utilization, could dramatically reduce the amount of mass we need to send from Earth. But in situ fuel production has never been done on another planet. It would require complex equipment operating autonomously for months or years in the harsh Martian environment. What if something breaks? What if the fuel production is slower than expected? What if the fuel quality isn't sufficient? The crew arrives at Mars only to discover that their ticket home isn't ready. That's not a risk. That's a nightmare scenario that mission planners lose sleep over. Another approach is to send multiple supply missions ahead of the crew, pre-staging everything they'll need. But each launch from Earth is expensive, and each one has a chance of failure. The more missions you need, the higher the cumulative risk that something will go wrong. And if a critical supply mission fails, what then? Do you scrub the crewed mission? Do you accept higher risk? These are billion-dollar decisions with human lives in the balance. Then there's the ascent vehicle itself, the rocket that will lift the crew off Mars. This vehicle needs to be reliable after sitting on the Martian surface for 18 to 20 months, exposed to temperature swings, dust storms, and radiation. Rockets are complex machines with thousands of potential failure points. Keeping one in launch-ready condition on Mars for that long is a monumental challenge, and there's no room for error. If the ascent vehicle fails, the crew is stranded. Game over. Actually, let's pause there for a moment and really sit with that thought. Stranded on Mars, it's the ultimate horror scenario for space exploration. You're on another planet with no way home, limited supplies, and a slowly ticking clock until something critical fails. Your life support runs out of spare parts, or your habitat develops a leak you can't fix, or a dust storm damages your solar panels and you lose power. The crew on Earth watches helplessly as you send your final messages across the void, knowing there's absolutely nothing they can do to save you. This isn't idle speculation. NASA and other space agencies have contingency plans, or at least discussions, about what happens if a Mars crew can't return. Would they stay on Mars, trying to survive as long as possible? Would there be provisions for, let's say, a dignified end if survival became impossible? These are questions nobody wants to ask, but they have to be asked. The stakes are that high. Let's dig deeper into something we touched on briefly, the Martian environment itself and how it complicates the return journey. Mars isn't just a static, lifeless rock. It's a dynamic world with weather, seasons, and environmental hazards that directly impact mission planning and astronaut safety. Understanding these factors is crucial because they determine not just whether you can survive on Mars, but whether you can leave. Dust storms on Mars are legendary. Unlike Earth, where storms are driven by temperature differences and moisture in the atmosphere, Martian dust storms are powered by solar heating and the planet's thin atmosphere. They can grow from local disturbances into planet-wide events that last for months. In 2018, a global dust storm covered the entire planet, blocking out so much sunlight that NASA's Opportunity rover, which relied on solar panels for power, went silent and never woke up again. That rover had been operating for nearly 15 years. A dust storm ended it in weeks. Now imagine you're an astronaut on Mars when one of these storms hits. Your solar panels, which provide power for your habitat, life support, and communication systems, are suddenly producing a fraction of their normal output. Dust is everywhere, coating every surface, infiltrating seals and joints despite your best efforts. The static electricity generated by blowing dust can damage electronics. Visibility drops to near zero, and you're stuck inside your habitat waiting it out, hoping your power reserves last until the storm clears. If you're scheduled to launch for the return journey and a major dust storm hits, you might have to delay. But delaying means consuming more supplies, using more life support resources, and potentially missing your launch window entirely. Launch windows are another critical constraint. You can't just leave Mars whenever you want. The orbital mechanics of interplanetary travel are unforgiving. Earth and Mars are constantly moving in their orbits around the Sun at different speeds. There's a period roughly every 26 months when the planets align favorably for a journey between them. Miss that window and you're waiting another 2 years. 2 years of extra supplies, extra life support consumables, extra wear on equipment, extra radiation exposure, extra psychological stress. The mission planners have to time everything perfectly, accounting for the outbound journey, surface operations, and the return window. There's very little margin for error. The Martian gravity itself, that 38% we keep mentioning, creates a unique challenge for the human body. It's not quite microgravity, but it's not Earth gravity either. Your body will adapt to it, finding a new equilibrium. Your bones will settle into a density that's sufficient for Mars, but inadequate for Earth. Your muscles will maintain enough strength to function on Mars, but not enough for Earth. Your cardiovascular system will calibrate itself to pump blood effectively in Martian gravity, but struggle in Earth's stronger field. You're essentially becoming a Martian, physiologically speaking, and the longer you stay, the more Martian you become, and the harder it will be to become Earthling again. Recent computational models published in 2022 examined orthostatic intolerance, the inability to stand without dizziness or fainting in the context of Mars missions. The researchers used mathematical simulations to predict cardiovascular responses during an active stand test after prolonged exposure to Martian gravity. The results showed that astronauts would indeed experience significant cardiovascular deconditioning, and the partial gravity of Mars would not be sufficient to prevent it. When these astronauts returned to Earth, their cardiovascular systems would be woefully unprepared for the demands of full gravity. This leads to a fascinating and somewhat disturbing question. Is there a point of no return? A duration beyond which the human body has adapted so thoroughly to reduced gravity that coming back to Earth becomes medically impossible. We don't know yet because we've never had humans in reduced gravity for years at a time. The longest any human has spent in continuous microgravity is 437 days, achieved by cosmonaut Valery Polyakov in the mid-90s. He returned to Earth and eventually recovered, though it took considerable time and effort. But Polyakov was in microgravity, not partial gravity, and his mission was less than half the duration of a Mars mission. We're extrapolating into unknown territory. Some scientists have proposed a radical idea. What if we don't bring them back? What if the first Mars missions are one-way trips? The crew would establish a permanent settlement, living out their lives on Mars. This would eliminate the enormous challenges and costs of return missions, allowing us to send more supplies and equipment instead of return fuel. It's not as far-fetched as it sounds. In 2012, a private organization called Mars One proposed exactly this concept, recruiting volunteers willing to leave Earth forever. The project ultimately failed due to financial and technical challenges, but it sparked serious discussions about the ethics and feasibility of one-way missions. From a purely engineering standpoint, a one-way mission is simpler and cheaper, but the psychological and ethical implications are staggering. You're asking people to volunteer for permanent exile, to never see their home planet again, never feel Earth's breeze or rain, never swim in an ocean, never hug their families in person. And what about their health without the possibility of returning to advanced medical care on Earth? Any serious health issue becomes a potential death sentence. Are we comfortable sending people to Mars knowing they'll likely die there, possibly from preventable or treatable conditions? Let's talk about another insidious problem: radiation damage to the central nervous system. We mentioned cognitive impairment earlier, but let's go deeper. High-energy particles, particularly the heavy ions in galactic cosmic rays, don't just damage DNA, they physically tear through brain tissue, destroying neurons and disrupting neural connections. A single heavy ion can traverse your entire brain, leaving a trail of damage in its wake. Your brain has about 86 billion neurons, so losing a few here and there might seem insignificant. But neurons don't regenerate well, and the effects are cumulative. Studies on rodents exposed to radiation similar to deep space conditions have shown alarming results. The animals exhibited increased anxiety-like behavior, impaired memory formation, and reduced social interaction. Neurological examinations revealed physical changes in brain structure, including reduced dendritic complexity. Dendrites are the branching extensions of neurons that form connections with other neurons. Reduced complexity means fewer connections, which translates to impaired cognitive function. If similar changes occur in human astronauts, and there's every reason to believe they would, we're talking about permanent alterations to personality, decision-making ability, and mental acuity. Imagine returning from Mars not just physically weakened but mentally changed. Your memories might be fuzzy, your problem-solving skills diminished, your emotional regulation impaired. You might struggle with tasks that were once second nature. And these changes could be permanent, a lifelong consequence of your journey to another world. Is that an acceptable price to pay for exploration? Different people will answer that question differently, but it's one that every Mars astronaut will have to confront. There's also emerging research on how space radiation affects the heart. For a long time, the focus was on cancer risk, which is certainly significant, but cardiovascular disease might actually be a bigger concern. Studies examining cause of death among Apollo astronauts who ventured beyond Earth's magnetic field to the Moon found a higher rate of cardiovascular disease mortality compared to astronauts who only flew in low Earth orbit or never flew at all. The sample size is small, so drawing definitive conclusions is difficult, but the trend is concerning. The Apollo missions lasted only days or weeks. Mars missions will last years. What will the cardiovascular consequences be? The mechanism isn't fully understood, but radiation appears to damage the endothelial cells that line blood vessels, promoting inflammation and atherosclerosis, the buildup of plaques in arteries. This process normally takes decades to develop on Earth, but radiation might accelerate it dramatically. An astronaut could return from Mars with the cardiovascular system of someone 20 or 30 years older. Heart attacks, strokes, and other cardiovascular events could occur much earlier than they otherwise would. And remember, this is on top of the cardiovascular deconditioning from reduced gravity. Your heart is both weaker and more damaged. That's a dangerous combination. Let's shift gears and talk about something more technical, but equally important: the actual trajectory and energy requirements for the return journey. Getting from Mars back to Earth isn't as simple as pointing your spacecraft homeward and firing the engines. You're dealing with orbital mechanics, the complex interplay of gravitational forces, velocities, and positions. There are several possible trajectory types, each with different energy requirements, travel times, and risks. The most fuel-efficient trajectory is called a Hohmann transfer orbit. You wait until Earth and Mars are in the right positions, then fire your engines to enter an elliptical orbit that intersects Earth's orbit at just the right time. It's elegant and efficient, but it takes about 9 months and requires precise timing. If you miss your launch window by even a few days, you might not be able to reach Earth, or you might arrive when Earth isn't there anymore. The math has to be perfect. There are faster trajectories called opposition class or fast transit trajectories. that can reduce travel time to 4 or 5 months, but they require significantly more fuel, which means more mass, which means a bigger rocket, which means more cost and complexity. And even 5 months is a long time to spend in microgravity enduring radiation exposure. Some mission plans try to split the difference using a moderately fast transit that balances time and fuel requirements. But every choice involves trade-offs. One of the most nerve-wracking moments of the return journey will be the trans-Earth injection burn, the engine firing that breaks you out of Mars orbit and sets you on course for Earth. This burn has to be precise. Too little thrust and you don't reach Earth's orbit. Too much and you might overshoot or come in at the wrong angle. Your spacecraft's engines have to work perfectly after sitting idle on Mars for months. Any malfunction during this critical burn could doom the mission. There are no second chances. You get one shot and it has to work. Once you're on your way back to Earth, you face another 7 months of all the problems we've discussed: radiation, bone loss, muscle atrophy, cardiovascular deconditioning, psychological stress. But now there's an added element of urgency. You're going home. You can see Earth growing larger in your window each day. The psychological dynamic shifts. On the outbound journey, you had the excitement of going somewhere new, the anticipation of landing on Mars, the thrill of exploration. On the return, you're exhausted, beaten down, desperate to get back. Time seems to move slower. Every day feels longer. The isolation and confinement become harder to bear because the end is in sight but still so far away. And throughout all of this, you're hoping, praying that nothing breaks. Your spacecraft is carrying you across millions of kilometers of vacuum. If a critical system fails, you can't pull over and call for help. You can't order replacement parts. You have to fix it with whatever you brought, relying on the ingenuity and expertise of your crew. Apollo 13 famously survived a catastrophic oxygen tank explosion through improvisation and determination. But Apollo 13 was only 3 days from Earth when disaster struck. Imagine the same scenario happening halfway between Mars and Earth. You're months away from any possible rescue, and rescue might not even be feasible. You either fix the problem or you don't come home. As we approach Earth after that grueling 7-month return journey, a new set of challenges emerges. Challenges that are in some ways even more dangerous than anything faced so far. Earth's atmosphere, which protects us so well from space, now becomes an obstacle that must be conquered with extreme precision. And the astronauts attempting this conquest are in the weakest physical condition of their entire lives. Let's talk about aerocapture and entry interface. When your spacecraft approaches Earth, it's traveling at approximately 11 kilometers per second. That's over 39,000 kilometers per hour, or about 32 times the speed of sound. At this velocity, even the thin upper atmosphere creates tremendous forces. The entry interface, typically defined as the point where the atmosphere begins to have measurable effects at around 120 kilometers altitude, marks the beginning of the most dangerous few minutes of the entire mission. The entry corridor, the range of angles at which you can safely enter the atmosphere, is remarkably narrow. Come in too shallow, and you'll skip off the atmosphere like a stone skipping across water, bouncing back into space with no way to return. Come in too steep, and the deceleration forces become unsurvivable, crushing the crew, and the heat becomes intense enough to vaporize your spacecraft despite its thermal protection. The acceptable entry angle is typically only about 2 degrees. 2 degrees between too shallow and too steep, between escape into space and incineration. Your navigation has to be absolutely perfect after traveling hundreds of millions of kilometers. During re-entry, the spacecraft is enveloped in a sheath of superheated plasma created by compression of atmospheric gases. This plasma is so hot and so ionized that it blocks radio communications completely. There's a period of several minutes called the communications blackout, where mission control has no contact with the crew. They can't send instructions, can't receive telemetry, can't do anything except wait and hope. The spacecraft is on its own, following pre-programmed instructions, with the crew inside experiencing forces and heat unlike anything in normal human experience. The heat is concentrated on the heat shield, a specially designed surface that protects the spacecraft through ablation. The material literally burns away in a controlled manner, carrying heat away from the crew compartment. The outer surface of the heat shield can reach temperatures exceeding 2000 degrees Celsius. For context, that's hot enough to melt iron. The engineering that goes into these heat shields is extraordinary, but it's also terrifying because any defect, any crack, any imperfection could allow heat to penetrate through to the crew compartment. The Columbia disaster in 2003 was caused by a breach in the thermal protection system. The consequences were catastrophic. Now imagine going through this ordeal after 3 years in space. Your body has been weakened by bone loss, muscle atrophy, and cardiovascular deconditioning. The G-forces during re-entry peak at around 4 to 6 times Earth's gravity, as we mentioned earlier. But let's really think about what that means. If you weigh 70 kilograms on Earth during peak deceleration, you effectively weigh 280 to 420 kilograms. Your arms feel like lead weights. Your chest is being compressed. Breathing requires conscious effort. Blood pools in your lower body, making it difficult for your heart to pump enough to your brain. Tunnel vision, grey out, even blackout are real risks. Astronauts returning from 6-month ISS missions have described re-entry as intensely uncomfortable, even painful. Scott Kelly, who spent 340 days on the ISS, wrote in his memoir about the intense burning sensation on his skin during re-entry, the difficulty breathing, the feeling that his body was being crushed. And Kelly, despite the long duration of his mission, was still better prepared than Mars astronauts would be. He had access to state-of-the-art exercise equipment throughout his stay. Mars astronauts will have had more limited resources and longer exposure to reduced gravity. There's a real concern that some Mars astronauts might not remain conscious throughout re-entry. G-force-induced loss of consciousness, or G-lock, occurs when the brain doesn't receive enough oxygenated blood. Fighter pilots experience this during high G maneuvers, and they train extensively to prevent it using special breathing techniques and pressurized suits. But astronauts during re-entry aren't pulling controlled maneuvers. They're strapped into their seats, relatively immobile, with weakened cardiovascular systems and no G-suits. If a Mars astronaut loses consciousness during re-entry, they're at the mercy of automated systems. And if something goes wrong, if a decision needs to be made, there's no one capable of making it. Let's consider the landing itself. Once the spacecraft has survived the heat and deceleration of re-entry, it still has to actually land. Different spacecraft use different methods. Apollo capsules used parachutes and splashed down in the ocean. The space shuttle landed like a glider on a runway. Modern capsules like SpaceX's Dragon use parachutes, followed by propulsive landing or ocean splashdown. The Soyuz uses parachutes and then fires retro-rockets just before touching down on land. Each method involves significant forces at touchdown. Even with parachutes and retro-rockets, the Soyuz landing is notoriously hard. Cosmonauts have described it as like being in a car crash. The capsule hits the ground at several meters per second, and occupants are jolted violently despite their harnesses and the seat's shock absorption systems. For astronauts returning from Mars with weakened bones, this impact could cause fractures. Your spine, your hips, your legs, areas already compromised by bone loss, are suddenly subjected to severe impact forces. Emergency medical teams need to be standing by, ready to extract the crew and provide immediate care. Ocean splashdown, while potentially gentler than ground landing, brings its own challenges. The capsule bobs in the water, subject to waves and motion. For astronauts who haven't experienced natural movement like this for 3 years, who are already dealing with disorientation and weakened vestibular systems, the rocking motion can cause intense nausea and vertigo, and they have to wait inside the cramped, hot capsule until recovery ships arrive. Depending on weather conditions and location, this could take hours of discomfort and medical vulnerability before they finally get help. But let's assume everything goes perfectly. The re-entry is successful, the landing is safe, the astronauts are conscious and alive. The hatch opens and they're greeted by recovery teams. Can they walk out? Almost certainly not. They'll be lifted out on stretchers carefully because their bodies can't support themselves yet. They'll be transported to medical facilities where teams of doctors, physical therapists and specialists are waiting, and then begins the long, arduous process of recovery and rehabilitation. The first few days back on Earth are particularly critical. Standing up causes severe orthostatic intolerance, as blood pools in the legs and the weakened heart struggles to maintain adequate pressure. Many returning astronauts can't stand for more than a few seconds without feeling faint. Simple movements are exhausting. Walking is like learning all over again because your muscles have forgotten how to work against Earth's gravity and your balance is completely off. Your bones are fragile. You need to be careful not to fall, not to bump into things because fractures are a genuine risk. Your immune system is suppressed, making you vulnerable to infections. Your vision might be impaired from the neuroocular changes. You might experience cognitive difficulties from radiation damage. You're essentially an invalid, completely dependent on others for care, despite being a highly trained, capable astronaut. The psychological impact of this helplessness after years of being an elite explorer can be devastating. Physical therapy begins almost immediately, but it's a slow process. Your muscles need to rebuild, your bones need to remineralize, your cardiovascular system needs to strengthen. Early sessions might involve simple exercises done lying down or in a pool where buoyancy reduces the stress on your body. Gradually, over weeks and months, you progress to standing, walking, light resistance training, and eventually more demanding activities. But you'll probably never be the same as you were before the mission. Studies of astronauts who spent extended time on the ISS show that some changes are permanent. Bone density in certain areas, particularly the hips and spine, may never fully return to pre-flight levels. The risk of osteoporosis and fractures remains elevated for the rest of your life. Cardiovascular changes might persist, increasing long-term risk of heart disease. The radiation exposure has increased your lifetime cancer risk by several percentage points. These are the costs, the permanent tolls that Mars explorers will pay. And we need to ask ourselves, is it worth it? What are we gaining that justifies these risks and sacrifices? The scientific knowledge, certainly. Samples from Mars could answer fundamental questions about the potential for life beyond Earth, about planetary formation and evolution, about the history of our solar system. The technological advancements required to send humans to Mars will drive innovation in countless fields, from materials science to medicine to artificial intelligence. The inspiration, the proof that humanity can achieve such an audacious goal, might spur a new generation to pursue science and exploration. But there's also something deeper, something harder to quantify. We explore because it's in our nature. Since the first humans left Africa tens of thousands of years ago, we've been spreading across the globe, crossing oceans, climbing mountains, venturing into the unknown. Space is simply the next frontier. Mars is the next horizon. Not going, choosing to stay confined to Earth forever, feels like giving up on something fundamental to the human spirit. We need to explore, to discover, to push boundaries. It's part of what makes us human. Yet we also need to be honest about the costs. The astronauts who go to Mars will sacrifice their health, possibly their lives, They'll experience suffering that no previous explorers have endured. They'll be guinea pigs, test subjects for humanity's expansion into the cosmos. We owe them not just our admiration, but our commitment to doing everything possible to protect them, to minimize the risks, to give them the best possible chance of not just reaching Mars, but coming home. This brings us to an important consideration that often gets overlooked in discussions of Mars missions: the political and economic realities. Space exploration is expensive, monumentally so. The Apollo program, which sent 12 humans to the moon between 1969 and 1972, cost approximately $25 billion at the time, equivalent to over $250 billion today. And that was for missions lasting only a few days each to a destination 3 days away. A Mars mission will be orders of magnitude more complex and expensive. Estimates for a crewed Mars program vary wildly, from $100 billion on the low end to over $1 trillion for a comprehensive, sustained exploration effort. That's money that has to come from somewhere, either government budgets or private investment. And maintaining political and financial support over the decades required to develop and execute such a program is extremely difficult. Administrations change, priorities shift, economic conditions fluctuate. The history of space exploration is littered with ambitious programs that were announced with great fanfare and then quietly cancelled when the bills came due. NASA's Constellation program, announced in 2004, aimed to return humans to the Moon by 2020 as a stepping stone to Mars. It was cancelled in 2010 due to cost overruns and budget constraints. The Space Launch System, NASA's heavy-lift rocket intended for deep space missions, has been in development since 2011 and has faced repeated delays and cost increases. As of 2026, it has flown only once, the uncrewed Artemis 1 mission. Getting humans to Mars will require sustained commitment on a scale rarely seen in human affairs. Private companies like SpaceX have entered the arena with bold promises and innovative approaches. SpaceX's Starship, a fully reusable Super Heavy launch vehicle, is specifically designed for Mars missions. Elon Musk has stated goals of sending the first crewed mission to Mars in the 2030s. But even with private sector involvement, the challenges remain immense. No amount of entrepreneurial enthusiasm changes the physics of radiation exposure or bone loss. The problems are real, and solving them requires time, resources, and breakthroughs that may or may not come when we need them. There's another dimension to the return journey that we haven't fully explored yet: the equipment and systems that need to function flawlessly for years in the harshest environment imaginable. Space hardware is subjected to temperature extremes, vacuum, radiation, micrometeoroids, and the relentless stress of operating far beyond any possibility of repair or replacement. Every component, every circuit, every seal has to work perfectly, not for days or weeks, but for years. The reliability requirements are almost impossibly stringent. Consider the life support systems. These aren't just keeping you comfortable, they're keeping you alive. They filter carbon dioxide from the air and replenish oxygen. They regulate temperature and humidity. They purify water for drinking and hygiene. They manage waste. Every single one of these functions is mission critical, and the systems must operate continuously for the entire duration of the mission. On the ISS, when a component fails, replacement parts can be sent up on the next cargo resupply mission, which launches every few months. On a Mars mission, there is no resupply. You have what you brought, and that's it. Redundancy is the standard approach to reliability in spaceflight. Critical systems have backups, and those backups have backups. But redundancy adds mass, and mass is your enemy. Every kilogram of backup equipment is a kilogram you can't use for something else: food, science equipment, radiation shielding, return fuel. Mission designers constantly wrestle with these trade-offs. How much redundancy is enough? How much is too much? Where do you draw the line between safety and practicality? And it's not just the big systems. Consider something as mundane as a pump bearing, a small mechanical bearing that allows a pump to spin. If that bearing seizes, the pump fails. If the pump is critical to cooling electronics or circulating air or moving water, then pump failure becomes a life-threatening emergency. You need spare pumps, spare bearings, tools to replace them, and crew members with the training to perform repairs. Multiply this across hundreds or thousands of components, and you begin to see the staggering complexity of maintaining a spacecraft for 3 years. Radiation doesn't just harm humans, it damages electronics too. High-energy particles can cause bit flips in computer memory, corrupting data or crashing systems. They can degrade semiconductors, reducing performance or causing outright failure. Spacecraft computers need special radiation-hardened components, which are typically years behind commercial technology in terms of performance and capability. And even radiation-hardened systems can accumulate damage over time. The longer the mission, the higher the probability of critical computer failures. Software is another potential point of failure. The systems controlling your spacecraft, managing life support, monitoring health, and navigating trajectories all run on software, millions of lines of code. And we know that all software has bugs. NASA and other space agencies have incredibly rigorous testing and verification processes, but it's impossible to catch every bug, every edge case, every potential interaction. The Apollo guidance computer famously experienced several program alarms during the first lunar landing. Fortunately, the flight controllers understood the errors and knew they weren't critical. But what if a software glitch occurs during a critical maneuver on the way back from Mars, and there's no mission control to help diagnose it in real time because of the communication delay? The spacecraft's propulsion system is perhaps the most critical single component. Without it, you can't correct your trajectory, you can't enter orbit around Mars, and most importantly, you can't come home. These engines must fire on command after sitting idle in the radiation and cold of space for months at a time. Rocket engines are complex, with turbo pumps spinning at tens of thousands of RPM, combustion chambers withstanding extreme temperatures and pressures, and intricate plumbing carrying volatile propellants. Everything has to work perfectly. Engine failures have doomed numerous unmanned missions. In a crewed Mars mission, an engine failure during the return journey would be catastrophic. Propellant management adds another layer of complexity. Rocket fuel and oxidizer need to be stored for years without significant boil-off or degradation. Cryogenic propellants like liquid hydrogen and liquid oxygen are incredibly challenging to store long-term because they're so cold that heat leakage causes them to evaporate. Some mission concepts use storable propellants like hydrazine or methane, which are easier to manage but have lower performance. Again, trade-offs. Better performance means less fuel needed, which means less mass, but more reliable storage means you're sure you'll have fuel when you need it. Which do you prioritize? Let's talk about something that might seem minor, but could have major consequences. Contamination. Spacecraft and spacesuits track Martian dust everywhere. This dust is incredibly fine, like talcum powder, and it's electrostatically charged, causing it to stick to everything. It gets into seals, into mechanisms, into electronics. The Apollo astronauts brought lunar dust back into their spacecraft, and it caused multiple problems: irritation to eyes and lungs, abrasion of suit materials, and interference with equipment. Martian dust is potentially even more problematic because it may contain perchlorates, toxic chemicals that could pose health risks. Inside the return spacecraft, contamination control is crucial. You can't have dust interfering with air filters, clogging valves, or abrading moving parts. Astronauts will need rigorous protocols for cleaning suits and equipment before bringing them inside, but perfect contamination control is probably impossible. Some dust will inevitably enter the habitat and spacecraft. Over time, it accumulates. Systems designed for clean environments start experiencing increased wear and tear. Filters clog faster, seals degrade sooner, small problems compound into bigger ones. There's also biological contamination to consider, although in the opposite direction. Planetary protection protocols are designed to prevent Earth organisms from contaminating Mars. This is both an ethical consideration — we don't want to destroy potential Martian life — and a scientific one. We need to be able to distinguish indigenous Martian biology from Earth contaminants. But humans are walking biomes. We're covered in and filled with trillions of microorganisms. Every breath, every touch, every bodily function releases microbes into the environment. Despite our best efforts at sterilization, humans will inevitably introduce Earth life to Mars. Some of these microbes might survive in protected microenvironments. Bacteria have been found living inside the ISS despite regular cleaning and the harsh conditions of space. Some species are remarkably resilient. If Earth microbes establish themselves on Mars, they could potentially spread, altering the Martian environment in unpredictable ways. This contamination could compromise scientific research for decades. And ironically, if we later discover life on Mars, we might never be completely sure whether it's native or whether we brought it with us. But let's return to the human element, because ultimately this is a human story. The crew dynamics over a 3-year mission are going to be absolutely critical to success. You're selecting a small group of people, probably 4 to 6 individuals, and asking them to live and work together in extremely close quarters for an extended period under conditions of constant stress and danger. These people need to be not just technically competent, but psychologically compatible. NASA has studied crew selection and compatibility extensively. Research on Antarctic stations, submarines, and space missions has identified key factors. You need people who can manage stress effectively, who communicate well, who can resolve conflicts constructively. You need cognitive flexibility, the ability to adapt when situations change unexpectedly. You need emotional stability, because breaking down psychologically is not an option when you're millions of kilometers from help. And you need people who can maintain motivation and morale even when conditions are grinding and monotonous. But here's the catch: you also need technical expertise across a wide range of disciplines. You need pilots, engineers, scientists, doctors. Each crew member needs to be cross-trained in multiple areas because your crew is too small to have specialists in everything. The commander might also be the primary pilot and have medical training. The mission specialist might be a geologist, an engineer, and a computer expert. Everyone needs to know how to perform emergency repairs, conduct EVAs, operate scientific equipment. The training regimen for a Mars crew would take years and would be incredibly intensive. And even after all that training, even after careful psychological screening, you're still putting human beings with human flaws and limitations into an impossible situation. Personality conflicts will emerge. Frustrations will build. Someone might develop depression, anxiety, or other mental health issues. Crew cohesion, the glue that holds the mission together, can deteriorate over time. Studies of isolated groups show that performance and morale often decline significantly in the second half of long-duration missions. There's actually a term for it: the third quarter phenomenon. People hit a psychological low point when they're past the halfway mark, but still far from the end. On the return journey from Mars, the crew will be in exactly this psychological danger zone. They're exhausted from months on the Martian surface. The excitement of exploration is behind them. They're physically weakened and likely experiencing health issues, and they still have 7 months of flight ahead, 7 months of confinement, boredom punctuated by moments of terror during critical maneuvers. Maintaining crew cohesion and mental health during this period will be one of the greatest challenges of the entire mission. Communication with Earth will help, but remember that delay. As the spacecraft travels back toward Earth, the communication lag decreases, eventually getting down to just a few minutes. But for most of the journey, real-time conversation is impossible. You send a message and wait minutes or tens of minutes for a response. This makes counseling and psychological support extremely difficult. A therapist can't have a normal session with a 20-minute delay between every statement and response. Crew members will largely be on their own psychologically, dependent on each other for support. Entertainment and recreation become surprisingly important. You need ways to relax, to decompress, to escape mentally from the confines of your spacecraft. Books, movies, music, games, all carefully curated and loaded onto the spacecraft's computers. But there's only so much content, and you'll go through it over 3 years. Astronauts on the ISS report rewatching favorite movies and shows dozens of times. Imagine being months into the return journey and you've exhausted every piece of entertainment you brought. The boredom can be crushing. Some mission concepts include virtual reality systems that could provide more immersive entertainment and even simulated environments that give the illusion of space and freedom. Imagine putting on a VR headset and experiencing a walk in a forest, or standing on a beach watching the waves. These psychological countermeasures could be crucial for maintaining mental health. But VR systems are heavy, they consume power, and they're another technological system that could fail. Once again, trade-offs. Let's consider the possibility of a medical emergency during the return journey. You're months from Earth, your body is weakened, and something goes seriously wrong. Maybe it's a kidney stone, an agonizingly painful condition that's more likely in space due to bone loss releasing calcium into your system. Maybe it's appendicitis requiring emergency surgery. Maybe it's a stroke or heart attack, conditions that are more likely after prolonged radiation exposure. Maybe it's a psychiatric emergency, a crew member experiencing a psychotic break. The medical capabilities aboard a Mars spacecraft will be limited. You'll have medications, basic surgical equipment, diagnostic tools, but nothing approaching what's available in a hospital. Treatment will be improvised, guided by telemedicine consultations with doctors on Earth who are working with incomplete information and significant communication delays. The outcome of any serious medical emergency is highly uncertain. And if a crew member dies during the return journey, the surviving crew members have to cope with that loss, that grief, while completing the mission. They can't turn back. They can't evacuate. They can only continue forward, carrying the body of their fallen crewmate and somehow maintain the psychological stability to pilot the spacecraft home. Death in space is something we don't like to think about, but it's a real possibility. If it happens, what do you do with the body? You can't simply jettison it into space. That would be ethically problematic and could contaminate the trajectory back to Earth. You probably preserve it, keep it in a cold storage area, and bring it home for proper burial. But having a dead body aboard, a constant reminder of mortality and loss, would be psychologically devastating for the surviving crew. As the spacecraft draws closer to Earth, another critical consideration emerges: planetary quarantine protocols upon return. This might seem counterintuitive. We're worried about Earth contaminating Mars, but now we need to worry about Mars contaminating Earth? Actually, yes, this is a serious concern that space agencies have been grappling with since the earliest days of planetary exploration. The probability that Mars harbors life is uncertain, but it's not zero. If there are Martian microorganisms, even extinct ones preserved in the soil or ice, astronauts might inadvertently bring samples back with them. These samples could be on their spacesuits, embedded in equipment, or collected intentionally for scientific study. The question is, could Martian life forms pose a threat to Earth's biosphere? Most scientists consider the risk to be extremely low. Mars and Earth are so different in terms of temperature, atmospheric composition, and available nutrients that organisms evolved for one environment would be unlikely to thrive in the other. But extremely low is not zero. and the potential consequences of introducing an invasive alien organism into Earth's ecosystem are so catastrophic that even a minuscule risk demands serious precautions. The Outer Space Treaty of 1967, which governs international space law, includes provisions for planetary protection. Article 9 specifically requires that space exploration be conducted so as to avoid their harmful contamination and also adverse changes in the environment of the Earth resulting from the introduction of extraterrestrial matter. This means that samples returned from Mars must be quarantined and thoroughly studied before being released into the general environment. The Apollo program implemented planetary quarantine procedures when astronauts returned from the Moon. The Apollo 11, 12, and 14 crews spent 21 days in quarantine after splashdown, isolated in a mobile quarantine facility and later in the Lunar Receiving Laboratory. These protocols were eventually discontinued for later Apollo missions as scientists gained confidence that the Moon was sterile. But Mars is a different story. Mars has conditions that could potentially support life. Water ice, organic chemistry, energy sources. The quarantine procedures for Mars returnees will need to be far more stringent. One proposal involves a dedicated orbital quarantine facility. The returning spacecraft wouldn't come directly to Earth's surface. Instead, it would dock with a space station specifically designed for quarantine operations. The crew would transfer to the station, and their spacecraft, along with all Martian samples, would be secured and sterilized. The astronauts would remain in orbit under observation for a period of weeks or months, while medical teams monitor them for any signs of unknown pathogens. Only after being cleared would they be allowed to return to Earth's surface. This sounds reasonable in theory, but consider what you're asking. These astronauts have just endured a 3-year mission. They've survived Mars, survived the return journey, and they're finally within sight of home. They can see Earth out the window, that beautiful blue marble, and now you're telling them they can't go home yet. They have to spend more time in space, more time in microgravity, while bureaucrats and scientists make absolutely sure they're not carrying Martian plague. The psychological burden would be immense. The alternative is ground-based quarantine, similar to the Apollo model but more comprehensive. The returning crew would land, probably in a remote area, and be immediately transferred to a high-security biocontainment facility. This facility would need to meet biosafety Level 4 standards, the highest level, designed for work with dangerous and exotic agents that pose a high risk of life-threatening disease. The astronauts would live in isolation, undergo extensive medical testing, and remain under observation for an extended period. Every bodily fluid, every exhaled breath, every waste product would be captured and analyzed for potential Martian organisms. From the astronauts' perspective, this must feel like imprisonment. After the heroism of traveling to another planet, after the sacrifices they've made, they're treated like vectors of disease, locked away from their families and the world. Yes, it's necessary for planetary protection, but it adds another layer of suffering to an already grueling experience. And remember, they're in terrible physical condition. They need intensive medical care and rehabilitation. Providing that care in a quarantine facility is more complicated and less effective than in a fully equipped hospital. The samples themselves, the rocks and soil brought back from Mars, present their own challenges. They need to be contained absolutely, with no possibility of even microscopic particles escaping into Earth's environment. NASA and ESA have been designing a Mars sample return facility for years. The current concept involves a building with multiple layers of containment, negative air pressure to ensure that air flows inward, and sterilization systems for anything that exits. Scientists would work with the samples using gloves built into the containment chambers or via robotic systems, never coming into direct contact. The analysis of these samples would be painstakingly slow. Every test must be conducted with extreme caution. Are there organic molecules? Are there structures that resemble cells or microorganisms? Are there any signs of metabolism or reproduction? These questions might take years to answer definitively. And until they're answered, the samples remain locked away, and by extension, so does some of the most exciting scientific data humanity has ever collected. But let's assume the quarantine period ends without incident. No Martian microbes are detected, or if they are, they're determined to be harmless. The astronauts are finally cleared to return to normal life, except their life will never be normal again. They are now among the most famous people on Earth, part of an incredibly exclusive club, humans who have walked on another planet. The attention, the expectations, the constant scrutiny will be overwhelming. Public appearances, interviews, documentary crews, book deals, speaking engagements, they'll be in demand constantly. Everyone will want to hear their story, to shake their hand, to be near someone who has done something so extraordinary. For some astronauts, this attention is energizing and rewarding. They become ambassadors for space exploration, inspiring the next generation. For others, it's exhausting and invasive. They just want to recover, to be with their families, to find some semblance of normalcy. But normalcy is no longer possible. Their relationships will have been strained or broken. 3 years is a long time to be away from a spouse, children, parents, friends. People change. Relationships that were strong before the mission may have weakened or ended during the long separation. The emotional distance created by hundreds of millions of kilometers is difficult to bridge. Some astronaut marriages have ended after long-duration missions. The Mars crew will face similar or worse challenges. And then there's survivor's guilt if something went wrong, if a crew member didn't make it back. The survivors will carry that weight forever. They'll be celebrated as heroes while privately grappling with the question, could we have done something different? Could we have saved them? Post-traumatic stress disorder is a real possibility for Mars astronauts, stemming from the constant danger, the near-death experiences during critical mission phases, and potentially the loss of crew members. Their careers as astronauts are likely over. You don't send someone to Mars twice, at least not with current technology. The health effects, the cumulative radiation exposure, the toll on their bodies, it's too much. They've given everything they had to give. Future missions will need new crews, fresh astronauts who haven't yet paid the physical price. So these Mars veterans face the challenge of figuring out what comes next. Do they stay involved with the space program in advisory or training roles? Do they pursue entirely different careers? How do you find meaning in normal work after you've been to another planet? Some might struggle with depression, with the feeling that the greatest achievement of their life is behind them and everything afterward is anticlimactic. The psychological term is post-mission blues, and it's common among astronauts. After the intensity, the purpose, the clarity of a space mission, returning to the ambiguity and mundanity of regular life can be deeply disorienting. For Mars astronauts who experience something even more profound than orbital missions, this letdown could be particularly severe. There's also the question of long-term medical monitoring. These astronauts are unique medical cases. Their radiation exposure, their prolonged time in reduced gravity, their experience with the Martian environment, all of this makes them subjects of intense scientific interest. They'll need to undergo regular medical examinations for the rest of their lives, tracking the long-term effects of the mission. Cancer screenings will be particularly important given their elevated risk. Every health issue they develop will be scrutinized. Is this a consequence of the Mars mission? Is this something we need to worry about for future crews? In a sense, they never stop being research subjects. Their bodies are data points in humanity's understanding of what space does to us. This is both a privilege and a burden. They're contributing to knowledge that will help future explorers, but their privacy, their medical autonomy, is compromised. Every illness becomes a matter of public and scientific interest. Let's zoom out for a moment and consider the broader implications of a successful Mars return mission. If astronauts make it to Mars and back, even with all the hardships we've discussed, it will be one of humanity's greatest achievements. It will prove that we can survive in deep space, that we can reach another planet, that we're not confined to Earth forever. The technological, scientific, and inspirational benefits will be immense, but it will also reveal the limitations. The health consequences will be documented in painful detail. Future mission planners will have real data about bone loss rates, radiation effects, psychological challenges, cardiovascular impacts. This data will inform decisions about how to make future missions safer, but it might also reveal that with current technology, Mars missions exact too high a price. We might conclude that we need to wait to develop better radiation shielding, artificial gravity systems, or faster propulsion before sending more crews. There's a scenario that keeps space planners up at night: a successful first mission followed by a catastrophic second mission. The first crew makes it back, battered but alive. Confidence is high. A second mission launches, but something goes wrong, something we didn't anticipate because we only had one data point. The second crew doesn't make it home. The political and public backlash would be devastating. The entire Mars exploration program could be cancelled, setting back human space exploration by decades. This is what happened with the Space Shuttle program. After 24 successful missions, Challenger exploded during launch in 1986, killing all 7 crew members. The program was grounded for nearly 3 years. Then, after returning to flight and completing 87 more missions, Columbia disintegrated during re-entry in 2003, killing another 7 astronauts. The shuttle program never fully recovered its momentum and was eventually retired in 2011. A Mars mission disaster could have similar or worse consequences because the stakes and costs are so much higher. Yet despite all these risks, despite everything we've discussed about the dangers and hardships, people will still volunteer. They'll compete fiercely for the opportunity to be part of a Mars crew. Why? Because the desire to explore, to push boundaries, to be part of something larger than ourselves is fundamental to human nature. The astronauts who go to Mars will do so with their eyes open, fully aware of the risks, accepting them as the price of the extraordinary privilege of being among the first humans to walk on another world. History will remember them. Their names will be taught in schools centuries from now, just as we remember Magellan, Columbus, Amundsen, Shackleton, and the Apollo astronauts. They will inspire future generations to reach even further, to push even harder. But we, the people sending them, have a moral obligation to give them every possible advantage, to invest in the research and technology that might bring them home safely, and to care for them when they return, broken but triumphant. The first human footprints on Mars will be one of humanity's defining moments, but the return journey, the struggle to bring those explorers home, will be equally defining. It will test our technology, our resolve, our humanity. And how we treat those returning heroes, whether we support them through their recovery and honor the sacrifices they've made, will say as much about us as a civilization as the fact that we sent them in the first place. Let's delve into something we've touched on but haven't fully explored: the economic and resource implications of not just sending people to Mars, but bringing them back. The return journey isn't just a technical challenge, it's an enormous drain on mission resources that fundamentally shapes every aspect of the endeavor. Understanding these constraints helps explain why some mission planners have seriously considered one-way trips and why the round-trip mission is so monumentally difficult. Think about fuel for a moment. To leave Mars and return to Earth, you need a tremendous amount of propellant. That propellant has mass, significant mass. And here's where the rocket equation becomes your enemy. The Tsiolkovsky rocket equation, formulated over a century ago, describes a brutal reality. The more mass you want to move, the more fuel you need. But fuel itself has mass, so you need even more fuel to lift that fuel. It compounds exponentially. Let's put numbers to this. Current mission concepts suggest that a Mars ascent vehicle, the rocket that launches astronauts from the Martian surface into orbit, would need to be roughly the size of the upper stages of a medium-lift rocket. We're talking about something with perhaps 15 to 20 tons of propellant to lift a crew capsule and a few astronauts into Mars orbit. That's 15 to 20 tons that had to be transported from Earth to Mars in the first place. But it gets worse. That Mars ascent vehicle wasn't just placed on Mars magically, it had to be landed, which required its own fuel for descent and landing. The lander carrying the ascent vehicle needed to be launched from Earth, which required fuel. The spacecraft carrying the lander needed fuel to slow down and enter Mars orbit. Every kilogram you want on Mars requires multiple kilograms of fuel at various stages of the journey. Some estimates suggest that for every kilogram you want to land on Mars, you need to launch 15 to 20 kilograms from Earth. The economics are staggering. This is why in situ resource utilization, or ISRU, is considered essential for Mars missions. Instead of bringing all your return fuel from Earth, you manufacture it on Mars using local resources. The most promising approach is the Sabatier reaction, which combines carbon dioxide from the Martian atmosphere with hydrogen to produce methane and water. The methane can be used as rocket fuel, and the water can be split into hydrogen and oxygen, with oxygen serving as the oxidizer. SpaceX's Starship is specifically designed around this concept. The plan is to land a propellant production plant on Mars ahead of the crewed mission. This plant would spend months, possibly years, slowly manufacturing methane and oxygen from Martian resources and stockpiling it for the return journey. By the time the crew arrives, their return fuel is waiting for them. It's elegant in theory, but enormously complex in practice. The ISRU plant itself is a sophisticated chemical processing facility that has to operate autonomously in the harsh Martian environment. It needs power, likely from solar panels or a small nuclear reactor. It needs to extract carbon dioxide from the atmosphere, which is thin and cold. It needs hydrogen, which probably means bringing it from Earth or extracting it from Martian water ice, which requires mining and processing operations. It needs to handle cryogenic temperatures to liquefy the methane and oxygen for storage. Every one of these systems is a potential failure point. And here's the terrifying part: the crew's lives depend on this plant working correctly. If they arrive on Mars and discover that the ISRU plant malfunctioned, that the return fuel wasn't produced, they're stranded. There's no backup, no contingency plan that can manufacture tons of propellant quickly. They would have to hope that a rescue mission could be mounted from Earth, which would take years to prepare and launch. More realistically, they would be waiting for a death that, while not immediate, would be inevitable once their supplies ran out. Risk management for Mars missions has to account for these single points of failure. One approach is redundancy. Send 2 ISRU plants, so if one fails, the other provides backup. But that doubles the cost and complexity of the precursor missions. Another approach is to extend the surface stay, giving the crew time to repair or rebuild systems if something goes wrong. But longer surface stays mean more supplies needed, more radiation exposure, and more psychological stress. Some mission architectures propose that the crew doesn't land until the return vehicle is fully fueled and verified operational. The astronauts would remain in Mars orbit while robotic systems confirm that the ascent vehicle is ready. Only then would they descend to the surface. This provides some safety margin, but it also means spending time in orbit around Mars, exposed to radiation without the slight protection offered by the planet's atmosphere, and regolith, waiting for confirmation that may or may not come. The energy requirements of the return journey are worth examining more closely. Getting from the Martian surface to Earth requires a velocity change, or delta V, of roughly 6 to 7 kilometers per second, depending on the specific trajectory and timing. For For comparison, that's similar to the energy required to reach low Earth orbit from Earth's surface. You're essentially launching into space all over again, but from Mars. Mars has advantages. Lower gravity and a thin atmosphere mean less energy is needed to reach orbit compared to Earth. But you're starting from zero velocity on the surface, and you need to reach a velocity of about 3.5 kilometers per second to achieve Mars orbit, then add more velocity to break free from Mars's gravity and head toward Earth. Every bit of that energy comes from burning propellant, which means mass you had to land on Mars or manufacture there. The return trajectory itself offers some choices. The most fuel-efficient path is a Hohmann transfer, which we mentioned earlier. But there are alternatives. A faster trajectory, using more fuel but reducing transit time, could be worth it if it significantly reduces radiation exposure and physiological degradation. Mission planners have to balance fuel costs against health costs. Is it worth carrying extra fuel, which makes the entire mission more expensive and complex, to shorten the return journey from 7 months to 5? How do you quantify the value of 2 months of reduced radiation exposure and physical decline? Some advanced concepts propose using Venus for a gravity assist on the return journey. By passing close to Venus, the spacecraft could gain velocity without burning fuel, potentially reducing travel time or propellant requirements. But this adds complexity to the trajectory and navigation. It also means passing through the inner solar system, where solar radiation is more intense. The crew would need better radiation shielding, which adds mass, which requires more fuel. Once again, you're balancing competing factors with no perfect solution. Let's talk about abort scenarios. In any mission, you need contingency plans for when things go wrong. Apollo 13 famously demonstrated the importance of abort capabilities when an oxygen tank explosion forced the crew to abandon their lunar landing and use the lunar module as a lifeboat for the journey home. Mars missions need similar abort options, but the distances and durations make them far more challenging. During the outbound journey to Mars, if a critical system fails, can you abort and return to Earth? In theory, yes, but it's not simple. Early in the mission, you might be able to turn around with a reasonable expenditure of fuel, but past a certain point, you're committed. Turning around would take more energy than continuing to Mars, swinging around the planet and using its gravity to slingshot back toward Earth. This is called a free return trajectory, and it was used as a safety feature in some Apollo missions. But for Mars, a free return might take years and expose the crew to even more time in space than completing the mission as planned. Once you're on Mars, the abort options are even more limited. If something goes catastrophically wrong on the surface, can you launch early and return to Earth immediately? Not if the planets aren't in the right positions. Orbital mechanics don't care about your emergency. If the next launch window is months away, you wait or you die. The only abort is to survive until the window opens, which means your abort plan is essentially just having enough redundancy and supplies to outlast the problem. During the return journey, abort options are essentially non-existent. You're committed to reaching Earth. If a system fails, you repair it or you work around it. There's nowhere else to go, no safe harbor. You can't abort to Mars, you've already left. You can't abort to the Moon, you're not passing close enough. Earth is the only destination, and reaching it is not optional. This lack of abort options represents a fundamental difference between Mars missions and anything humans have attempted before. Even on the Moon, Earth was only 3 days away. A severe emergency might be survivable long enough to get home. From Mars, Earth is months away under the best circumstances. You either solve the problem with the resources at hand, or you don't survive. The psychological impact of this reality is profound. Every astronaut on a Mars mission knows, intellectually and viscerally, that they are more isolated and more vulnerable than any humans in history. This knowledge affects decision-making, risk tolerance, and mental state. Some people might find it paralyzing, others might find it clarifying. Crew selection needs to identify individuals who can function effectively under this existential weight. Let's consider the scale of the infrastructure required to support a Mars return mission. On Earth, you need launch facilities capable of sending heavy payloads to Mars. You need mission control facilities that can operate continuously for years, with teams monitoring every aspect of the spacecraft and crew health. You need communication networks, the deep space network of large radio antennas that maintain contact with the spacecraft across the solar system. You need research facilities developing the technology, testing life support systems, simulating Mars conditions, training crews. You need manufacturing facilities building the spacecraft, the landers, the habitats, the rovers. You need supply chains sourcing specialized materials and components. You need political support maintaining funding through multiple budget cycles and administrations. The ecosystem required to support a Mars mission involves thousands of people and billions of dollars sustained over decades. And all of this infrastructure is required not just to send people to Mars, but to bring them home. A one-way mission could eliminate much of this complexity. You don't need return vehicles, return fuel, or the infrastructure to produce it. You don't need a spacecraft designed to keep people alive for the return journey. You send supplies and equipment instead. The mass savings are enormous, allowing you to send more people or more equipment for the same launch cost. This is why one-way missions keep coming up in serious discussions, despite the ethical concerns. From a purely engineering and economic standpoint, they're vastly simpler. But from a human standpoint, they're asking people to accept certain death, just with the timing uncertain. You're creating a small outpost of humanity on Mars, but you're also condemning those people to die there. No matter how we romanticize the idea of Martian pioneers, we're talking about people who will never see their families again, never experience Earth's environment again, and will likely die from medical conditions that would be treatable on Earth. Society has to grapple with whether this is acceptable. Are there circumstances where sending people on one-way missions is ethical if they volunteer, fully informed of the consequences? Is that sufficient? What about when things go wrong, when people change their minds, when the reality of permanent exile sets in? We would be creating a situation with no reversibility, no rescue option. History is full of exploration ventures that ended in tragedy and death, but those explorers always had at least a theoretical chance of returning. A one-way Mars mission eliminates even that chance. The societal and philosophical implications of Mars exploration, particularly the return journey, extend far beyond engineering and physiology. When we send humans to Mars and attempt to bring them back, we're making statements about our values, our priorities, and our vision of humanity's future. Let's explore these deeper dimensions. First, there's the question of who gets to go. Mars missions will be incredibly expensive, whether funded by governments or private entities. Only a handful of people will be selected from potentially millions of applicants. What criteria should determine who gets this opportunity? Pure merit based on skills and qualifications? Diversity to represent humanity's breadth? Political considerations to maintain international cooperation? Wealth, if private funding dominates? The Apollo astronauts were predominantly military test pilots. White American men selected for their technical skills and ability to perform under pressure. They represented a specific slice of humanity at a specific moment in history. Mars missions in the 21st century will face different expectations. There will be pressure to include women, to include people from different nations, ethnicities, and backgrounds. This is not just about fairness, it's about symbolism. The first humans on Mars will represent all of humanity, or at least that's the aspiration. But diversity can complicate crew dynamics, different languages, different cultural norms around hierarchy and communication. different expectations about privacy and personal space. These factors can create friction in close quarters over long durations. At the same time, diversity can strengthen crews by bringing different perspectives and problem-solving approaches. Mission planners have to balance idealistic representation against practical crew cohesion. There's also a gender-specific consideration worth examining. Women may actually be better suited for long-duration space missions in some respects. On average, women are smaller and require fewer calories, meaning less mass in food and life support requirements. Some research suggests women may lose bone density at slightly lower rates in microgravity. And studies of mixed-gender crews in isolated environments generally show better social dynamics than all-male crews, with reduced aggression and better conflict resolution. But there are complications. Radiation exposure is a greater concern for women because they have higher lifetime cancer risks from the same exposure levels, particularly for breast and ovarian cancer. Pregnancy in space is another consideration. While crew members would be carefully screened and contraception would be available, the possibility exists. Pregnancy during a Mars mission would be catastrophic. The radiation exposure would almost certainly cause severe developmental problems in a fetus, and medical resources aboard would be completely inadequate for prenatal care or childbirth complications. These biological realities force uncomfortable conversations about reproduction rights and bodily autonomy in the context of mission safety. Can you require crew members to use contraception? Can you require certain medical procedures before the mission? Where is the line between reasonable mission requirements and unacceptable intrusions into personal medical decisions? These aren't just hypothetical questions, they're real issues that will need clear policies before crews launch. Let's consider the geopolitical dimension. Space exploration has always had political undertones. The Apollo program was fundamentally driven by Cold War competition between the United States and Soviet Union. Today's space environment is more complex, with multiple nations and private companies involved. A Mars mission might be an international collaboration, with astronauts from NASA, ESA, Roscosmos, CNSA, JAXA, and others sharing the journey. International cooperation brings advantages, shared costs, pooled expertise, diplomatic benefits of working toward common goals, but it also brings complications. What happens if geopolitical tensions on Earth escalate while your crew is on Mars? If two nations represented on the crew go to war with each other back on Earth, does that affect crew dynamics? Can astronauts maintain professional relationships and trust when their home countries are in conflict? History offers cautionary examples. During the Space Shuttle era, American astronauts and Russian cosmonauts worked together professionally despite ongoing tensions between their governments. The ISS partnership has survived numerous political crises, but a Mars mission is more isolated, more vulnerable, and longer in duration. The psychological pressure of representing a nation, perhaps feeling responsible for maintaining diplomatic relationships through your personal behavior, adds yet another layer of stress to an already impossibly stressful situation. There's also the question of jurisdiction and law. Under the Outer Space Treaty, no nation can claim sovereignty over Mars. But what laws govern behavior on Mars? If a crew member commits a crime, who has jurisdiction? The mission commander? The nation that launched the spacecraft? The astronaut's home country? Maritime law offers some precedents. Ships at sea operate under the flag of their registration, but space law is still evolving. More troubling, what if there's a serious conflict between crew members, a physical altercation, a psychological breakdown leading to violence? In the confined environment of a spacecraft or Mars habitat, with no police, no courts, no ability to separate people safely, how do you handle criminal behavior? The crew would effectively have to act as police, judge, and jailer for one of their own. The mission commander would face impossible decisions with no good options. These scenarios may seem far-fetched, but they're not impossible. The psychological pressures we've discussed can break people in unpredictable ways. There have been incidents on Antarctic research stations, on submarines, and in other isolated environments where individuals have committed violent acts. A Mars mission lasting 3 years creates ample opportunity for psychological deterioration. Mission planners must have protocols for these worst-case scenarios, even if discussing them publicly is uncomfortable. Let's return to the return journey specifically and consider what it means symbolically. The journey home represents closure, completion, survival. It's the difference between a successful mission and a tragic one. In storytelling terms, the hero's journey requires a return. The hero ventures into the unknown, faces trials, gains wisdom or treasure, and returns to share it with their community. A Mars mission that ends with the crew stranded or dead feels incomplete, tragic, like a story with the final chapter torn out. This is why the return journey carries such psychological and cultural weight. It's not enough to reach Mars. We need to demonstrate that we can come back. We need to prove that space exploration isn't a suicide mission, that we can venture out into the cosmos and return safely. This proof is essential for public support, for political will, and for inspiring future generations to continue exploring. But there's a tension here. The more we emphasize the return, the more we're admitting that Mars isn't yet a place where humans can truly live, only visit. We're tourists, not settlers. The return journey is a retreat, an acknowledgement that Earth remains our only true home. Some space enthusiasts find this limiting. They envision Mars as humanity's second home, a destination not just to visit, but to colonize permanently. From this perspective, obsessing over the return journey is defeatist, missing the larger vision. Elon Musk and others advocating for Mars colonization often frame it in existential terms. Humanity needs to become a multiplanetary species to ensure long-term survival. If a catastrophe, whether natural or human-caused, destroys Earth's biosphere, a self-sustaining Mars colony could preserve human civilization. In this framework, early missions are just the beginning. The goal isn't to visit and return, it's to establish permanent human presence. But establishing that permanent presence requires solving all the problems we've discussed, not just for a 3-year mission, but indefinitely. You need to create a closed-loop life support system that can run for decades. You need to manufacture not just rocket fuel, but everything else needed for survival: food, water, air, medicine, spare parts, building materials. You need enough people to create genetic diversity and maintain specialized knowledge across generations. You need governance structures, economic systems, social institutions. A self-sustaining Mars colony is orders of magnitude more difficult than a temporary mission. The return journey, challenging as it is, provides a safety valve. If things go wrong, you can leave, but a permanent colony has no such option. You're betting that you can solve every problem that arises using only Martian resources. Given what we know about the health effects of low gravity, radiation exposure, and the psychological challenges of isolation, it's not clear that humans can thrive on Mars long-term with current technology. Children born on Mars would face particularly severe challenges. Development in 0.38 G would almost certainly affect bone and muscle growth, cardiovascular development, and possibly brain development. These children might never be able to visit Earth. Their bodies would be adapted to Martian gravity and unable to function in Earth's much stronger pull. They would be, in a very real sense, a new branch of humanity, Martians rather than humans. The ethical implications of creating a generation of people permanently confined to another planet, unable to experience the world of their ancestors, are staggering. These long-term considerations might seem beyond the scope of discussing the return journey from an initial Mars mission, but they're intimately connected. The return journey represents a choice. We're choosing to maintain our connection to Earth, to treat Mars as a destination rather than a new home. That choice carries implications for how we design missions, allocate resources, and think about humanity's future in space. Some argue we should focus on making the return journey as safe and reliable as possible before we even consider permanent settlement. Prove we can visit Mars routinely the way we visit Antarctica before attempting to live there permanently. Others argue this approach is too conservative, that we should aim for permanent settlement from the beginning, accepting higher risks in pursuit of the transformative goal of becoming a multiplanetary species. There's no clear answer. Different people, different organizations, different nations will have different priorities. What's certain is that the decisions we make about Mars exploration in the coming decades will shape humanity's relationship with space for centuries. The first return journey from Mars, whether it succeeds or fails, will be a defining moment in that story. Let's consider the media and public attention surrounding a Mars return mission. The journey home will be watched by billions. Real-time updates on the crew's condition, on spacecraft systems, on the countdown to Earth re-entry. The world will hold its breath during the communications blackout as the spacecraft plunges through the atmosphere. The moment when contact is re-established, when we know whether the crew survived, will be experienced collectively by a significant fraction of humanity. This level of attention is both beneficial and burdensome. It maintains public interest and support for space exploration. It creates cultural moments that inspire and unite people across divisions. But it also puts enormous pressure on the astronauts and on mission control. Every decision is scrutinized. Every problem becomes a public crisis. Privacy is impossible. The crew's struggle to survive and return home becomes entertainment, content, drama for public consumption. There's something uncomfortable about this voyeuristic aspect. We're watching people endure genuine suffering and risk death, but from the safety of our homes, experiencing it as a spectator sport. If a crew member dies during the return journey, their death will be broadcast globally. Their final communications might be shared publicly. Their family's grief will play out under intense media attention. We like to think we would handle this respectfully, but media coverage of disasters often prioritizes sensationalism over dignity. The astronauts know this going in. They understand that they're not just explorers, but also performers, representatives, symbols. Their mission is public in a way that almost no human experience has ever been. They have to maintain composure, professionalism, and inspirational attitudes, even when they're exhausted, frightened, and suffering. It's yet another layer of pressure on top of the physical and psychological challenges. Let's bring this all together by examining what a successful return from Mars would actually mean for humanity and what comes after that first triumphant landing back on Earth. Imagine the moment. After 3 years, after all the suffering and struggle we've discussed, the crew capsule appears as a streak of light across the sky. Re-entry is always violent. The spacecraft is traveling at 11 kilometers per second, protected only by a heat shield that must withstand temperatures exceeding 1,500 degrees Celsius. For Mars returnees, after years in space with weakened bodies, the deceleration forces will be brutal. They'll experience multiple Gs of force for the first time since leaving Earth, pressed into their seats as the atmosphere slows their descent. There's a communications blackout during re-entry. The plasma sheath surrounding the spacecraft blocks radio signals. Mission control loses contact. The world waits. Those few minutes of silence feel eternal. Everyone watching knows that things can go wrong during re-entry. We've lost spacecraft and crews during this phase before. Columbia. Soyuz 1, Soyuz 11, the margin for error is razor thin. Then contact re-establishes. The parachutes deploy successfully. The spacecraft is visible on tracking cameras. It's going to make it. The relief is overwhelming. After everything that could have gone wrong over 3 years, the radiation, the equipment failures, the psychological strain, the health deterioration, The million ways people could have died, they made it home. The landing might be in the ocean, like Apollo, with recovery ships standing by. Or it might be on land, like Soyuz, with helicopters rushing to the touchdown site. Either way, the hatch is open and the crew emerges into Earth's environment for the first time in 3 years. The gravity is crushing. They literally cannot stand unaided. Medical teams carefully extract them from the capsule and place them on stretchers. They're alive, but they're broken. The images of their extraction will be broadcast worldwide and will become iconic. People will see the reality of what deep space does to human bodies. The astronauts will look gaunt, aged beyond the years they've been gone. They'll be unable to walk. They may be unable to sit up without support. This is humanity's triumph and humanity's price, displayed simultaneously. After medical stabilization and initial treatment, assuming they clear quarantine protocols without incident, comes the long road to recovery. Physical rehabilitation will take months, possibly years. They'll need to rebuild bone density, muscle mass, and cardiovascular capacity. They'll work with physical therapists daily, gradually progressing from assisted movement to independent walking to eventually approaching their pre-mission capabilities. Some functions may never fully recover. Cognitive effects will also need monitoring. Radiation exposure can cause long-term changes in brain function, memory problems, processing speed reduction, mood regulation issues. These effects might not manifest immediately but could emerge months or years after return. The astronauts will need neurological and psychological monitoring for the rest of their lives, but they'll also experience profound gratitude and appreciation for Earth. After years in the sterile, confined, hostile environment of spacecraft and Mars habitats, Earth is paradise. The air is breathable without equipment. Water falls from the sky. Plants grow in abundance. There are birds, insects, clouds, wind, weather, seasons, the endless variety and richness of Earth's biosphere. Things we take for granted become precious when you've been deprived of them for years. Many astronauts report a changed perspective after spaceflight, often called the overview effect. Seeing Earth from space creates a profound sense of the planet's fragility and unity, a recognition that borders and conflicts are meaningless when viewed against the backdrop of the cosmos. Mars astronauts will experience this amplified. They've been further away than anyone in history. They've experienced firsthand how hostile the universe is to human life. Earth's uniqueness and value will be viscerally clear to them in ways that those of us who've never left can barely comprehend. This perspective will shape how they spend the rest of their lives. Many will likely become advocates for environmental protection, planetary stewardship, international cooperation, the things that seem obviously important when you've seen Earth as a fragile oasis in an endless void. Their voices will carry weight. They've been to another planet. They've survived what no one else has survived. People will listen. The success of that first return mission will also shape the future of space exploration. If the crew makes it back safely despite all the challenges, it proves that Mars missions are survivable. Public and political support for continued exploration will strengthen. Plans for second, third, and subsequent missions will accelerate. Infrastructure that was experimental becomes operational. Techniques that were theoretical become proven. The pathway to Mars becomes clearer, but success doesn't mean easy. Each subsequent mission will face similar challenges. The radiation doesn't diminish, the low gravity doesn't increase, the psychological stress doesn't disappear. Every crew will pay a similar physical price. Over time, we'll accumulate more data, refine our approaches, develop better countermeasures. But the fundamental problems we've discussed won't be fully solved until we have breakthrough technologies. Faster propulsion reducing transit time, effective radiation shielding, artificial gravity systems. or medical treatments that can counteract space-induced health effects. Some of these breakthroughs may come from Mars mission research itself. The urgent need to protect astronauts could drive innovation in radiation protection, with applications on Earth for cancer treatment. Research into bone loss could advance osteoporosis treatment. Closed-loop life support systems could inform sustainable living technologies. The psychological research could improve our understanding of human resilience and mental health. Space exploration often generates unexpected benefits that justify the investment beyond the exploration itself. There's also the inspirational dimension. The return of the first Mars crew will be a moment of collective human achievement. In an era often dominated by division, conflict, and cynicism, it will demonstrate what humanity can accomplish when we work toward common goals. Young people watching will be inspired to pursue careers in science, engineering, medicine, and exploration. Some of them will be the astronauts, engineers, and mission controllers for future missions. This inspiration has tangible value. Studies of the Apollo program's impact found that it significantly increased the number of students pursuing STEM education. Those students became the scientists and engineers who drove technological innovation for decades. A successful Mars mission would likely have similar or greater impact, creating a generational wave of people motivated to push the boundaries of what's possible. But we also need to be realistic about the costs. The resources devoted to Mars exploration are resources not spent on other priorities: poverty alleviation, disease eradication, climate change mitigation, education, infrastructure. This is the perennial debate about space exploration. Is it worth it? Are we justified in spending billions to send a handful of people to another planet when so many problems remain unsolved on Earth? There's no universally correct answer. People of good faith disagree based on different values and priorities. Those who support Mars exploration argue that pushing technological boundaries, expanding human knowledge, and ensuring long-term species survival justify the cost. Those who oppose it argue that we should solve Earth's problems before venturing elsewhere, or that robotic exploration provides most of the scientific benefit at a fraction of the cost and risk. What's undeniable is that if we do send humans to Mars, we have a moral obligation to bring them back. We're asking people to risk everything for the sake of exploration and advancement. The least we owe them is every possible effort to ensure their return. This means adequate funding, rigorous testing, conservative decision-making when safety is at stake, and comprehensive post-mission care. Cutting corners to save money or accelerate timelines is unacceptable when lives are at stake. The return journey from Mars represents the completion of a promise. When we select astronauts and send them on this mission, we're implicitly promising to do everything in our power to bring them home. Technology, medicine, mission planning, training, support systems, all of it directed toward fulfilling that promise. Whether we succeed depends on our commitment, our ingenuity, and frankly, a measure of luck. Space is unforgiving, and even perfect planning can't eliminate all risks, but the attempt itself is meaningful. Humans have always explored beyond safe boundaries, driven by curiosity, ambition, and the desire to expand our horizons. Mars represents the next frontier in that eternal human story. The return journey, with all its challenges and risks, is what makes the story complete. It transforms an expedition into a round trip, a venture into a survivable mission, a dream into a reality. When that first crew walks off their recovery transport onto solid ground, when they're reunited with their families, when they share their experiences with a world that watched their journey, we'll have achieved something profound. We'll have proven that humans can travel to another planet and return. We'll have pushed the boundaries of human endurance and technological capability. We'll have created a new chapter in the human story, one that future generations will study and build upon. And perhaps, in the process, we'll have learned something important about ourselves, about our resilience, our capacity for cooperation, our ability to overcome seemingly impossible challenges. These lessons apply not just to space exploration, but to all the other challenges we face as a species. If we can send people to Mars and bring them home, what else might we accomplish if we commit our resources and ingenuity? The return from Mars isn't just about completing a mission, it's about proving what's possible when humanity reaches for the stars. And in that reaching, in that striving, we discover not just other worlds, but something essential about ourselves. If you found this exploration fascinating and want to dive even deeper into whether humans could actually survive and live on Mars long term, I invite you to watch the video on the screen, where we explore the realities, challenges, and possibilities of making Mars not just a destination to visit, but a place to truly call home.